So 21, which is a driver going around a corner. Oh, so we know right away if they go around a corner, they're accelerating, right? And we want to know what the force exerted by the static friction is. Okay, so this would be one that would kind of fall into forces and other concepts. Because you got forces going on here, but you also have circular motion. So I'm going to use just a generic form, but I'm going to include a good force diagram with it. So 21. Let's see. I'm picturing the road kind of like this, and here's our car, and the car is going in this direction. But we know, of course, that it's accelerating towards the center of the curve, right, in that direction. That's just kind of keep my eyes straight. That's not my force diagram. My force diagram I'm going to do from kind of a side view here, because I know it has weight down, normal force up. It's going to have a frictional force on it, which will be towards the center of the circle, and it's going to be accelerating towards the center of the circle, and its velocity at this point is into my board. So I do that back view of an arrow, right? Back of the head and the crosshairs. So this would be my force diagram I'd be looking for. And then probably the written part would be, since traveling in a circle must accelerate towards center, and in this one, friction provides net force. So kind of a half and half. All right, but I got to show that I understand why there has to be a net force on this. Good? All right. Now, it's always good to tell, what do they want to know? What force exerted by the static friction? Okay. So, I'm going to come down here. Everyone saw I posted a new rubric for the house? Good. So, let's see. Equations I'm going to pull from the equation sheet is Newton's second law, and I'll probably pull it A sub c equals v squared over r. Right from the equation. I think those are the only two I'm going to end up needing. So I'm going to start off by looking in the x direction, because that's where my frictional force is and my acceleration and everything like that. So we'll of course start off then we'll go in just the x direction. Are you guys okay if I call to the left positive? In my diagram, to the left is positive. Okay. So my only force is my frictional force, and that equals m and times my positive acceleration, which happens to be towards the center of the circle. And let's see, they want to know that. Do they tell me the mass? Yes. Do they tell me the radius? Yes. Do they tell me the speed? Yes. Oh. And they just want to know the frictional force. So I just substitute in now. 1800 Oh, I probably should have done one more step, substituting in there v squared over r. 12 meters per second. A lot of people will forget and drop the squared there. So be careful of that. And 65 meters. And I find my frictional force in Newton. Now, probably one other factor I should have put in my y is the frictional force. Remember, it's that interesting factor that it will never create motion. It's as large as it's required to be. So hopefully, well, since it doesn't skid, we know that the frictional force can be as large as the force needed for it to go around the circle. If we didn't know that it didn't skid, maybe this force would be larger than the frictional force, and therefore that's when you skid. But we're pretty sure, so you can do the math. Any questions on this one before we move on? Excellent. All right, so number 9. The ball is clicked at this angle above the horizontal and it's caught at the same level as it was kicked. What is its initial speed? All right. So we know the ball is a projectile, so that's why I would start off with just your generic y. So I would start off, ball is a projectile. Bless you. Thus, only influenced by gravity. And this is where I might, I know the ball is going to follow a parabolic path like this, and its velocity here at the beginning is some velocity v, but I know it's at an angle of, what did they tell me, 65 degrees or something? 65. And because they tell me things like it was caught at the same height that it was launched, I know that the initial y velocity will be equal but opposite to final y velocity. Oops. I should move that over. Right? That's only true if it takes off and lands at the exact same height. Any other heights, that's not true. But might as well use it because this one takes off and lands at the same height. It might prove useful to us. Alright, so equations I'm going to need. Well, I might need my general kinematics. Right? Vector, 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 vector. I think I'm going to need that the final equals the initial plus a delta t. So those are the two I'm grabbing from my equation sheet. And I'm going to draw that initial velocity again. I'm going to draw its components. So this was 65 degrees, so this is v naught. adjacent, so cosine 65 degrees, and this side is V naught sine 65 degrees. So, I'm going to use that little factoid that I wrote down in blue above, because when it starts off, it's going up at V naught sine 65 degrees, and because it comes down at the exact same height, it's coming down at V naught sine 65 degrees, right? Right, because it's down. And I know that that happens, for me, 4.3 seconds later. So I'm just going to use V final equals V initial plus A delta T. I know it's only influenced by gravity, so I know it's acceleration. So I have negative V naught sine 65 degrees equals V naught sine 65 degrees, because taking up is positive, plus negative 9.81 meters per second squared, because I know it's a projectile, times 4.30 seconds. And all I have to do there is solve for V naught. And there was much rejoicing. Alright, so we got Jill of the jungle swinging on a vine that is 7 meters long. Now I'm assuming that she's swinging like the vine is above her. So, what is the tension of the vine? Whose mass? If Jill, whose mass is this, is moving at this when the vine is vertical. So I'm assuming she's at the bottom and the vine is above her. So again, this will be a forces but other concepts. So here's my detailed drawing of Jill. And there's the vine. So we know she's accelerating this way because she's in circular motion. Kind of do that. But her weight is going to be down. And there's going to be a tension upwards. This is 22. So Jill is in circular motion, thus accelerates towards center. Tension provides net centripetal force. Good? Yes? No? Maybe? Alright. So, let's see. Newton's second law. Centripetal acceleration related to speed and radius. So, this time I'm just going to do the forces in the y direction. Which way do you guys want to call positive? Up towards the center or down away from the center? Up towards the center, is that good? Okay. So let's see, I had a force of tension upwards, so positive plus a negative weight or force of gravity. Oh, that's the other one I should probably have grabbed from my equation sheet, right? I haven't memorized it by now. Equals m and then AC, because that's my acceleration that way. And I think they wanted me to solve for the tension, right? So rearrange this, get F sub t equals MAC plus F sub g. And then m v squared over r plus mg. And then I know everything. I can solve for my tension in newtons.